In this lesson, we're going to begin talking about solving quadratic equations. When solving a quadratic equation, you will find the x-intercepts of the graph. That's basically the highlight of what we're going to be talking about over the next couple of lessons. So the goal in solving a quadratic is to determine where your parabola or your quadratic function is going to pass through that x-axis. The x-intercepts have three other names to them, and you may have heard these before. The names are solutions, roots, and zeros. Anytime you hear solutions, roots, and zeros, it's just another way to say the x-intercept of the graph. We'll be using those terms quite a bit in the next couple of sections. So a couple things to know before we actually start solving. All x-intercepts have a y-coordinate of 0. So when you're solving a quadratic, you can substitute a 0 in for the y or f of x if you're in function notation. And I have a nice visual over off to the left here of showing you this, where anytime you have a point that's on the x-axis, you can see that each of those three coordinates there have a y value of 0. And don't forget, you can graph all equations in Desmos and view their x-intercepts. We're going to be talking about some different methods on how to solve a quadratic, but remember, you can always plug it into Desmos and check yourself to make sure you're getting the exact location of where that graph crosses the x-axis. Now let's look at these examples here below. These are possible intercepts of a quadratic equation. Now, these three graphs don't represent all graphs that we're going to see. It's just how you could possibly see them. You could have a quadratic graph that passes through the x-axis twice. What that would mean is that you're going to have two intercepts, or you're going to have two solutions. You could also have a graph that only passes through the x-axis once. And it has a special name here, and it's called a double root. And the last graph that you could potentially run into is one that actually doesn't cross the x-axis. This is when your quadratic function has no solutions at all. And we'll take a look at what that looks like here soon. Okay, so now that we have some vocabulary, let's go ahead and talk about the first method on how to solve a quadratic. This should look really, really familiar to you because we spent an entire unit talking about factoring. So let's go ahead and talk about how to solve a quadratic using the factoring method. Looking at this first example here, you notice first that our quadratic is in standard form. One of the key things about pretty much every topic in this unit is that you want to put your function in standard form most of the time. So when factoring, you want to go ahead and do that. So one other thing I want you to notice is, do you notice how we are set equal to 0 here? So if you're solving a quadratic, remember, you can substitute 0 in for y. All right, now let's go ahead and solve this by factoring. What I'm going to do is simply, I'm going to do exactly what I've done in the factoring unit. I'm going to go ahead and ask myself, is there a GCF? Which I do not have. But I do have a trinomial, don't I? I do have a trinomial, and my A coefficient is 1. So I know that I have to use my little tool here to find the two numbers. Remember the two numbers? So if I were to multiply 1 times 15, that's going to give me my top number. And then my bottom number is going to be that center number. There it is. And we want to figure out two numbers that multiply to give us 15, but they add to give us -8. You're probably thinking of -5 and -3. Now, let's create the factors. My factors here are going to be x minus 5 and x minus 3. But don't forget, the whole equation is set equal to 0. So I'm going to go ahead and set it equal to 0. Up to this point, there's nothing really new. But now we're going to add in this property at the bottom. This is called the zero product property. Basically what you're doing is you're going to be setting each apparent factor, which is basically just a factor, equal to 0 to determine the solutions of the quadratic. So when we're factoring and you get your factors, though we call them factors, but when we're solving a quadratic, looking for the solutions, these turn into what we like to call apparent factors. And what we're going to do is take each one of them and set them equal to 0. Let me show you what I mean. I'm going to go ahead and take x minus 5 and I'm going to set it equal to 0. And I can simply go ahead and just solve this. And you can see that that's going to give me an answer of x is equal to 5. This is one of my solutions. This is where the graph's going to cross the x-axis. I'm going to write that above in coordinate form. Remember, when you're writing something in coordinate form, your y is going to be 0 because it passes through the x-axis. So my coordinate is 5, 0. My other one is going to be found by taking my other apparent factor, and I'm going to set that equal to 0 as well. That's going to give me x is equal to 3. That is my other solution. I'll go ahead and write that one in coordinate form as well. If I were to take this quadratic equation and put it into Desmos and graph it, it would pass through the x-axis at 5 and 3. And that's how you factor and solve for the solutions. Let's go ahead and try another one. In the next example, you can see that I am not in standard form. So let's go ahead and put ourselves in standard form. And I'm just going to do that by adding 27 to both sides. And I'm just going to kind of scoot it over to the other side so that I am in a nice standard form. So I'm going to say plus 27 is equal to 0. Now let's go ahead and factor. I asked myself first, do I have a GCF? And I do have a GCF. So let's go ahead and pull out the GCF of 3. When I factor out the 3, I'm left with x squared minus 6x plus 9. And that whole thing is equal to 0. We can continue factoring this just like we would normally. I can see that my piece on the inside here is a trinomial with a coefficient a is 1, meaning that I can go ahead off here to the side and I can break this down. So I'm looking for two numbers that multiply to give me 9 and they add up to give me -6. Those numbers are -3 and -3. So let's go ahead and break this down. Here's my GCF, and here are my two factors, x minus 3 and x minus 3. I'm going to set that equal to 0. Now at this point, there's nothing new. But now we're going to apply that zero product property, and we're going to set each of these apparent factors equal to 0. Notice how I have 3 apparent factors here. Here they are. Now, if we try to set 3 equal to 0, well, that doesn't make sense because those two numbers are not equal. When you have an integer by itself like this and there's no variable, then you cannot set that apparent factor equal to 0. It doesn't work. So you really just kind of disregard it. Now let's go ahead and take x minus 3 and set it equal to 0. So x minus 3 is equal to 0. And if I add 3 to both sides, you can see that that leaves me with x is equal to positive 3. I'm going to write that as the coordinate of 3, 0. Now, it would seem kind of silly to do that whole thing again, since the other apparent factor is the same. So what you're going to notice here is that this is called a double root. Do you see how I have 2 of them there? This is a double root, meaning that this quadratic only has one solution, and it's only going to pass through the x-axis once. It's kind of cool. So in that first example, our quadratic passed through twice, but in this example, it's just going to pass through once. And that's how you solve a quadratic using factoring. Now, those are just 2 examples, but remember, we learned a lot of different factoring techniques in the last unit. So as you work through different problems like this, you might be using different factoring techniques that are not shown here in the lesson. So just be on high alert and be ready for all those different factoring techniques. Okay, now I'm going to show you how to go backwards, okay? Now I want to show you this before I show you the other method today. Here it says, determine the apparent factors of the quadratic equation. Now this time I'm actually giving you a graph and I want to know, well, let's think about going backwards. If I give you the solution, could I determine what the apparent factors are? Well, let's look at the first one here. Now, remember that the solution to a quadratic is where the graph crosses the x-axis. So it looks like I have 2 solutions in this first problem. Now, you can see that this first solution is x is equal to -1. In order to get the apparent factor that this solution came from, I need to do the zero product property backwards. Essentially, what I need to do is I need to change the sign. Remember, if I have an apparent factor of x plus 1, if I set this equal to 0, it's going to give me a solution of -1, which is what I want. So one of my apparent factors is x plus 1. Looking at the other one, I can see that my solution here is x equals 3. In order to get the apparent factor, I have to basically take the opposite operation, so x minus 3. Because if I set that equal to 0, it would give me that solution of 3. So my 2 apparent factors in this situation are x plus 1 and x minus 3. Let's look at this other one. Here I have 2 solutions again, or 2 roots, or 2 zeros, whatever you want to call them. Now, this one over off to the right is kind of easy because we see that x is equal to 2. And we can simply just change that into x minus 2 to get our apparent factor. So x minus 2 is one of our apparent factors. But what about this one over here? Do you notice how this is at x is equal to 0? When I have something like this, x is equal to 0, that is your apparent factor because you cannot change that into something like x plus 2 or x minus 2. It's just x equals 0. So this apparent factor is going to be recognized by just writing an x. It's kind of like you're going backwards from factoring. Okay, and the last thing I want to show you today is another method on how to solve a quadratic. This is by taking the square root of both sides. So, one thing we need to note here is if the bx term in the standard form of a quadratic equation is not present, meaning it is not there, you can use this method. That's why this method is very valuable. You can also factor it and get the same answer. Okay, so you can do this, these 2 problems by factoring or this method that I'm about to show you, and you'll still get the same answer. But I'm going to show you this new method so that you have a lot of tools for your toolbox. So let's look at this first example. Okay, now this is a situation where when you're using this method, we actually don't want to be in standard form. It really doesn't matter what form we're in, because what we want to do is first recognize that we do not have a bx term. When you figure that out, you want to move your constant over to one side of the equal sign, and you want to move your x squared term to the other. So watch what I'm going to do. I'm going to simply subtract 10 from both sides. In doing that, I'll end up with 16x squared is equal to 64. The goal here is to solve for x, because that is where your graph crosses the x-axis. So let's go ahead and do that using our equation skills and divide both sides by 16. That will leave me with x squared is equal to 4. Now, this is a heavy algebra concept. When you get rid of a square, the only way to do that is to take the square root of both sides. When doing that, what happens is the square root and the 2 cancel each other out, and you're left with x. Now, when dealing with quadratics, we are no longer just working with the principal root, meaning the positive root, because we all know that the square root of 4 is 2. We know that. But it's actually also negative 2, because doesn't 2 times 2 equal 4? And negative 2 times negative 2 also equal 4? Well, this is when we actually start applying the positive and the negative root. So the square root of 4 is going to give us an answer of plus or minus 2. And this is your answer. What it means is your graph is going to cross through the x-axis at positive 2 and negative 2. We could write this in coordinate form like we did in the past couple of slides, or we could write this in roster form. If you remember, roster form are those little squiggly brackets with a plus, minus, and a 2. That's another way you could write your answer. Okay, let's try another one. So in the next one, we recognize that we do not have a bx term. So we are set up and ready to go to solve this by taking square roots. So I'm going to go ahead and move my constants over to one side. I usually like to move it over to the right side. It's just out of habit. So I have 3x squared, and then equals, whoops. And looking over this problem, I think I have a little mistake in my actual problem. So let's just go back real quick here. I apologize for this. But let's go ahead and change this 4 to a 3. I think that's going to affect it a little differently. Okay, let's go ahead and subtract 3 from both sides. I think that's going to do what I intended it for it to do. So 3x squared equals negative 12. Now, I'm going to divide both sides by 3, just like before. And this time, x squared is going to be equal to a negative 4. To get the x by itself, we're going to take the square root of both sides. Now, this is weird, because we've never taken the square root of a negative number before, because for right now, it's impossible. You cannot find two numbers that multiply to give you negative 4. So in this situation here, where you have x is equal to the square root of negative 4, that it's impossible. You can't do it. So if you have a situation that ends like this, that means that you are going to have no solution. And what that means is that this particular quadratic equation is not going to pass through the x-axis. We could write this in roster form like this. And that's how you solve a quadratic, by taking the square root of both sides. And I think that is all, but we are going to be talking about a couple more methods on how to find the x-intercepts of a quadratic function in the lessons to come.